All right. So this talk is going to be asynchronous because it's going to execute out of order. It's going to be something like, when should I use it? How does it work? And then by the time you've seen how it works, you'll kind of understand what it is. So my name's Jesse Davis. I work for MongoDB here in New York City.
Hi, Jesse. Hi, Jesse.
Hi, guys. Yeah. As you may know, in New York, there's three kinds of food. So we have sub sandwiches, pizza by the slice, and omakase, which is a word meaning something like chef's choice. It's when you go into a sushi restaurant and they give you whatever is good that night. So New York is a crowded place, and there's a lot of scaling difficulties with serving all the people, but each kind of food has a different scaling challenge. So first of all, when you want to get a sub, you go to the counter, and a sandwich maker comes out of the sandwich maker pool. And you both go to the counter, and you tell the sandwich maker what kind of sandwich you want, what ingredients, and you have this synchronous one-on-one interaction which lasts for the duration of the entire sandwich making process. The sandwich maker doesn't talk to a different client, doesn't take a break. That person is completely dedicated to you until the sandwich is done and you walk away with it, at which point the sandwich maker returns to the pool and then maybe takes the next client off of the eater queue. So this is sort of like a CPU-bound web service where each client request requires a lot of computation, but no external resources in order to satisfy it. And in that case, you should have, say, a thread or a process per request which handles the entire request from start to finish before it begins on another request. So this is an example of the kind of application that does not benefit from async, because there's no idle time during the course of completing a client request. Just use multiprocessing to handle this problem. There's no advantage to concurrency whatsoever. But a different kind of food has different kinds of scaling problems. So let's examine pizza by the slice next. So it starts the same. You go up to the pizza counter and you tell the pizza cook what kind of slice you want. And the slices are already made. They're just a little bit lukewarm. So the pizza cook puts the pizza in the oven and waits for 2 minutes until the slice is hot, at which point the cook returns the slice to you, hot, and you walk away happy. Now, what happens if there are multiple clients who all want pizza at the same time? You can't really scale this out by adding more pizza cooks. In the previous example, if we had more sandwich makers, you could make more sandwiches until you run out of space behind the counter, right? So it's like, if you have more CPUs, you can serve more requests by adding more processes. Here, that doesn't work because most of the time is spent waiting for the pizza to be hot. And the cook isn't actually doing any work during that time, so there's no point adding more cooks. Instead, the cook should be async. The cook should be rapidly switching between various tasks as they become ready. So as a client comes in, the cook asks, what kind of slice do you want? As a slice becomes hot, the cook gives it to the client who's waiting for it. The bounding resource here is the cook's ability to remember which slice goes to whom and how long it's been in the oven. The cook has to remember the state of all of these in-flight processes. So this is more like a normal web application. A client request comes in, the web server looks at the request, makes some external request to a database or to an OAuth provider or some other kind of web service over a socket, and then it has to wait for the response. And this is the kind of application that benefits the most from async. Because if you were to assign a thread to every incoming request, that thread is going to spend most of its life just waiting for the backend so that it can process that backend result, like the result of a database query or an OAuth transaction, in order to be able to respond to the original client and send the request back where it came from. So if you have lots of in-flight operations at once, having a thread for each is wasteful. It would be better to have a single process or a small number of processes that are able to rapidly switch among various tasks as they become ready. And so this is what async is for. And this reduces the amount of memory per in-flight operation or per connection and allows you to scale it to a larger number of connections per server. So the final kind of food is omakase. And in omakase, you go up to the counter with your friends, and the waiter tells the kitchen that people have shown up. And the kitchen doesn't need any more information than that. The kitchen just starts making sushi, and the waiter brings it from the kitchen to the clients as it becomes ready. And again, adding more waiters would be wasteful. You don't need a waiter per client, and if you did, you'd run out of space behind the counter. The same way if you had a thread per connection, you would run out of memory. It's better to have one waiter who sees sushi becoming ready in the kitchen and takes it to the proper client at the proper time. And this is like a newfangled WebSocket application. If you go to gmail.com and open a WebSocket connection to Google's server, nothing else happens. You're both just waiting around for new email to show up. And when an email arrives on Google's side, it sends that information down to you over the WebSocket. And since WebSockets are very long-lived, that means that Google has a huge number of WebSocket connections open at a given time. It can't possibly support tens or hundreds of thousands of threads per server, but if it has an async WebSocket server listening, then it can easily support tens or hundreds of thousands of clients at once because it's not spending a thread per each. So that's kind of like when to use it is if you're serving slices of pizza or sushi, you need async, and if you're serving subs, don't bother. Clear, right? So, this problem is called C10K for the 10,000 concurrent clients problem. It was written by a guy named Dan Kegel, or Kegel, I'm not sure which. The paper's maybe 8 or 10 years old now, but it's still really good and it's worth a read. He says, it's time for web servers to handle 10,000 clients simultaneously, don't you think? After all, the web is a big place now. And he says that perhaps in the not too distant future, those who prefer using one thread per client will be able to use that paradigm even for 10,000 clients. Nevertheless, at the current time, if you actually want to support that many clients, you're probably off using some other paradigm. So that's still true today. Threads still aren't as efficient as async servers at this kind of problem. So this is what async is for, is to handle this level of concurrency efficiently. So that's what it's for. And we're going to try like a provisional definition of what is it. So my definition of async is that it's single-threaded I/O concurrency. So you don't have parallel computation because you're single-threaded, but you can have multiple I/O events in flight with an async server and handle them concurrently. Async frameworks use non-blocking sockets. We'll see what that means in detail in a few minutes. And it registers for events on those sockets with OS-level facilities. On Linux, it's called ePOL. On BSD, it's called KQ. Windows has something called IOCP. And the async framework uses an event loop. In Twisted, it's called a reactor. And the event loop or the reactor continuously discovers new events that have occurred and dispatches those events to event handlers. So there are many other definitions of async that don't match this, but when we're talking about twisted or node or tornado, and we say that they're async, this is what we mean. It's because they fit this description. So there's a new async framework. It's called Async IO, and it just got pushed into the Python 3.4 standard library. It was mainly written by Guido with about a dozen other people. I made a few small contributions, which were the most exciting code I've ever written in my life. It conforms to a PEP called 3156, which describes its purpose and its interfaces. And Async IO provides, it's much like Twisted or Tornado, it's influenced by both. And it provides a standard event loop. So the years, the decades of incompatibility among various asynchronous frameworks in Python means that a lot of code has to be written again and again and again. So like the MongoDB driver had to be written once for multi-threading, and again for Tornado, and then again because I wanted to do it, and then again for Twisted, and on and on and on. Async IO is meant to start to unify the various async frameworks by giving a single event loop interface and an implementation that lives in the standard library. It also provides coroutines, and they're amazing, and we are not going to talk about them because there's no time. So to begin with, I know that that's pretty small, but we're going to make an example application, and we're going to build it on Async IO. So the application is just a simple chat app. So we've got two independent web server pages, and they're connecting to the backend over WebSockets. And you can see that whenever a message comes from one of them, it's sent to the server over a WebSocket, and the server rebroadcasts it to anybody else who's connected. This is absolutely the stereotypical async example. There's nothing special. So we're going to walk down through the layers of how this works. The first is a few lines of my own example code in the application layer. Beneath that, there's a WebSocket implementation. And here, Async IO follows Twisted's terminology. So we have the same idea of a protocol, which decides what bytes to send, and a transport, which knows how to send and receive bytes. So a protocol is like WebSockets, and a transport is like TCP. And Async IO provides you with some transport wrappers, so it gives you a way to talk TCP. And it defines what a protocol should do, but it doesn't actually give you any protocols. So the Async IO that's in the standard library doesn't even have an HTTP implementation. You cannot make a web server out of it as it is. So it's not batteries included, it's low level. If you want any protocols, you have to get them from a third party. And in this case, I'm getting a WebSocket protocol from a library called Autobahn. Beneath that is the event loop, which is watching for events and executing event handlers. And then beneath that is the layer that we won't actually see how it works. It's the selectors module, which is also new in Python 3.4. And it actually talks directly to the operating system and registers for event notifications on non-blocking sockets. So with all of that said, we can now actually start to look at some code. We'll start simple. We'll import the protocol and the protocol factory from Autobahn for WebSockets. Just like Twisted, Async IO has you create protocols and then protocol factories. And the factory gives you a new instance of the protocol every time you connect to something. The next thing we do is we need to make a subclass of the WebSocket protocol. This is our chat protocol. It has a global list of clients, and it overrides 3 callbacks that are defined by Autobahn. One is executed when a new client connects, and we just add ourselves to the global list. The next happens when somebody sends us a message, and we just iterate through all the clients, and we broadcast the message to everybody except ourselves. And onClose is executed when a client disconnects, and we remove ourselves from the global list when that happens. So that's very straightforward. The final thing we need to do, I buried the lead. This is the promise that I'm going to make to you. In the next 10 or 12 minutes, I'm going to explain to you how it is that an event on a socket causes onConnect to be executed. So this is going to be the how async works part of this talk. Is you're going to see how we receive a connection from a client, register for event notifications, and finally cause onConnect to be executed. And if we understand that, then we'll understand how async works. So the first thing we need to do is see how a server is created. So that's at the bottom of my example application here. We create a protocol factory, we attach a protocol to it, we get the event loop from Async IO. We finally then do the important thing, which is we create the server. That should say, let's look at this. Maybe I need to narrow my slides. They should go out on diet. So the create server, it takes the interface that it's going to bind to, and it's here. So now we're a layer below where we were. We're out of my example app, and we're in Async IO itself in the standard library. Create server, it creates a listening socket. It binds it to an interface. That stuff is all very standard and not specific to async, so I've just put ellipses in there. The interesting part starts when we call set blocking false. And that tells the OS, for this socket, any operation I attempt should either succeed or fail instantly, but it should never block. So if I call receive on a socket and there's no data to be received, whereas ordinarily my thread would go to sleep until data came in this case, I receive an exception immediately instead, that there's nothing to read. After that, I get the socket's file descriptor. It's just a number. And I register it with the selector. So the selector is that super low-level layer that we're not going to explain, but we can see what it does, which is it takes a file descriptor and an event mask. And the mask tells it what events we're interested in. So we want to know when this socket becomes readable, because that will tell us that a new client has come in to connect. And then we register you can pass in any data at all as that final argument, and you'll get it back later. So what we're going to put in are 2 callbacks, a reader and a writer. And one will be executed when the socket is ready for reading. So that is the accept connection, which will handle the event of a client connecting to us. And then the writer is none. So yeah, the next step is to look at accept connection. So we've created a server, we've handed it a protocol, it started listening, and now we're going to see what happens when somebody tries to connect to it. Here it is. We're still in the standard library here, and it takes that listening socket and it calls accept on it. And this doesn't block because we set it non-blocking, and we're only executed when we know that there's actually a client at the other end waiting to connect to us. So we can call accept now, and we get a new connection, which represents one end of the connection to the client. And we set that non-blocking as well because it's a new socket. And we instantiate a protocol using the protocol factory. And that is the chat protocol that we defined back in our application. This is the special subclass of the WebSocket protocol that we got from Autobahn. We pass that into the transport along with the connection. And the transport there, you can see it has an init function, which calls its superclass. And then there at the bottom, it calls protocol.connectionMade. And that was what we wanted to see. We wanted to understand how it was that a client connecting to us on a non-blocking socket would cause an event to execute an event handler. And so now we've seen how that happens. We're not totally done yet with how does async work, because there's one part that I kind of waved my hand about. And that was accept connection. How exactly does Async IO realize that a socket has become readable? So to do that, we need to look at the very last line of our example application, which started the event loop. This is like Twisted's reactor.run. It's loop.run forever. And we're going to look at its implementation as the final piece of this explanation. So back in the standard library now, here's run forever. And as expected, it's a while true loop. And it gets an event list out of the selector. So again, this is magic, but we know what it does, which is that it returns us a list of things that have happened or things that are ready to be examined, events that we told the selector we were interested in. And that list comes as a list of triples, the file descriptor, the event mask, which tells us what happened, and then that data that we passed in when we registered, which is the reader and the writer callback. So the next thing there is we unpack the data to get the reader and the writer callback, and then we check, does the mask have the read bit set? That means that the socket became ready for reading. So we add the reader callback to a queue of runnable callbacks called ready. And then we do the same for writing. Does the event mask have the write bit set? If so, then we take the writer callback, if there is one, and we add that to the ready queue. Finally, we've examined everything in the event list, and we check how many callbacks are runnable. So that's n to do. And for that number of callbacks, we pop them off the beginning of the queue and execute them. And this loop looks weird. It should be just like for callback in ready, execute callback. The reason why we check the number that are runnable at the beginning of this loop is because these callbacks can be anything, and they can do anything, including registering new ready callbacks. So by the time we're done with this loop, there might be more callbacks added. And it's an important aspect of Async IO's event scheduling that only the callbacks that were ready by the time we reached the bottom of this main loop are going to be executed now. Any that become ready during the course of this cycle won't be executed until the next iteration. And that makes lots of things simpler and fairer. So I believe that I have explained how async works. Quick review, we start a server. The server binds the socket and registers its file descriptor and tells the event loop to execute accept connection when the descriptor becomes ready for reading. Then we return to the application, which calls loop.runForever. Run forever finds out that a client has connected, and it calls accept connection, and that calls back into our application and calls on connect. So this is going much faster than I feared. So to review, Async IO uses non-blocking sockets, which is a means of telling the operating system not to block me if I'm waiting for some piece of I/O that's not ready. There's an event loop which tracks the association of sockets to event handlers that are waiting for events on those sockets. And it uses some operating system level API to register for event notifications. And that's all hidden in the magical selectors module, which you don't really have to understand. The event loop uses selectors to receive event notifications and executes callbacks when those occur. So now we can re-examine the when should I use it question, because we really understand how it works and what it is now. So use it if you have a WebSocket application, because those tend to have a very large number of concurrent connections. And the same if you have a slow but high throughput backend, or just any situation in which you have a very large number of concurrent connections, but you're not doing much computation. Don't use it if you are doing a lot of computation, because it will add complexity without much benefit. Also, anything that you talk to that does I/O, whether it's a database or a web service, it needs a driver that's written for your async framework. So if you don't have an async driver for your database or whatever, don't use async, because they won't work together and you'll get worse performance than if you just went multi-threaded. And finally, it's a little harder to write. So if you don't have expertise in shop or you don't have the time to build it, just use multi-threading and save async for later. If you have a WebSocket aspect to your application, then you can mix and match, making a multi-threaded server for some parts of your application and a WebSocket specialist server for the long-lived connections that your clients give you. So that is that. I have a minute or 2 minutes and 40 seconds for questions. I want to take 2 questions and then I want to ask you 2 questions. So let's go.
Hey, Jesse. When you mentioned that it's only implemented in Python 3 and it's part of the standard, I thought we had the answer to his question about why Twisted has not yet been written for Python 3, and that I thought the answer might be because it's already written in Async IO in the standard library. But then you said it doesn't include protocols, and I thought there may be another answer, which is that Twisted is now being written on Async IO, and they were waiting for the standard to be stabilized. But assuming...
So I don't know their plans. That is one of the things that's going to happen, is that Twisted will be able to replace its reactor with the Async IO event loop. But I think that the whole Twisted package is also slowly being ported to Python 3 as well, and it's just big and old, and it takes a long time.
But if it is, assuming it is eventually ported, how will someone who wants to take advantage of the asynchronous programming model and who thinks they're in the yes category, how will they decide between using native Async IO and using a package like Twisted?
I really don't know. That's a great question. It will depend on what third-party libraries you want and what kind of performance numbers come out once they're comparable. Question way back there. How does this affect the lives of people who use greenlets or gEvent or coroutines? So gEvent is supposed to be compatible at some point with Async IO's event loop, and that will allow gEvent and non-gEvent async code to interoperate within a single process and not block each other. So that's going to be fantastic. And coroutines, I'm not talking about in this talk. So I'm going to ask you guys 2 questions. Number 1 was I spent many minutes on the submarines pizza omakase food joke. Did that help, or is that a waste of time, and should I do something else? So useful. Waste of time, I should use it for something else. Oh, okay, it was useful. Great. And the other question was, raise your hand if I basically answered the 3 questions. What is it? How does it work? And when should I use it? So yes, I answered the questions for you. Ooh. And no, I did not. Oh, okay. And then abstain? Okay. All right. Thank you very much, guys.